Hello and welcome to today's webinar. Today's topic is very exciting and interesting. ArcFault is ETAP's new module for the simulation of arc faults or arc flash in medium and high voltage systems. This webinar is packed with information on the background and industry needs for the ArcFault module. We will discuss the model validation and development, plus go over some of the assumptions that were made for its creation and use. ArcFault is not simply a static application, but it's a fully integrated product within the ETAP ArcFlash family of products. And we will be able to observe simulations of arc faults placed at different voltage levels and equipment types. This will include single-phase arc faults, line-to-line arc faults, or three-phase arc faults. We will also discuss through the presentation how ArcFault was designed to help engineers provide reasonable yet conservative estimates for arc flash events in enclosed equipment between 15 to 36 kV. Last, we will introduce the ArcFault calculator, which is a very powerful tool, which is part of the ETAP 18.1 release, which will follow our current ETAP 18 release, and we will discuss how this powerful calculator can be used to interface with even third-party databases. Before we get started, we'd like to talk about the need for ArcFault and how that came about. First of all, utilities were required by Osha to perform incident energy calculations for voltages above 1,000 volts or starting at 1 kilovolts. The other reason for the proliferation of and the need for this module is the increase in the application of renewable energy systems, and in particular for their AC collector systems, which tend to operate between 15 to 38 kV. Because of these reasons and others, ETAP decided to actively pursue the development of an arc flash calculation module which will be better suited to provide instant energy results at these voltage levels. So before we get into the modeling of the actual arc and its physical behavior, let's talk a bit about the need for ArcFault. As we all understand, as linemen approach live distribution electrical circuits, either by climbing poles or by approaching them using boom trucks or elevator trucks, these electrical workers approach different arc flash boundaries. These boundaries are the distances at which the incident energy is approximately 1.2 to 2 calories per centimeter square, or even higher. And this, of course, depends on the arc rating of their personal protective equipment. Once the electrical workers cross these boundaries, they are exposed to a variety of potential arc faults. In overhead transmission systems, these arc faults may include series on-load arc faults, which occur as disconnecting equipment operates. They could be exposed most commonly to line-to-ground arc faults, and of course, less likely, but still possible, line-to-line arc faults, and perhaps even three-phase open-air arc faults, which will be, of course, considered the least likely possibility. As we can see in this slide, we have images of electrical workers performing disconnection of ground and switches, and of course arc fault events occur. The distance between the face to ground mode and the electrical worker is considered the main dominant factor in the calculation of the thermal energy which reaches the person working on that energized circuit. Here we have other examples of electrical or live tasks which are performed by electrical workers around high voltage equipment. The important thing to note here is that as the system voltage changes, these gaps increase, and the behavior of the arc faults will be dominated by the gap between conductors and the fault current levels that are present in that electrical system. However, as electrical workers cross these boundaries and approach the equipment, they come near the potential arc faults. Here we see that the ArcFault program or module could also be applied to the determination of instant energy levels, not only for overhead distributions, sub-transmission and transmission systems. However, the program could also be used for the analysis of arc faults in substations, in particular open air substation equipment. In these slides, we see some examples of electrical workers performing different energized work around three-phase circuits in open air conditions. One thing that you should note in this particular slide is the potential distance between ground and the phase conductor, and the potential for an arc fault to occur between these 2 points, which will be the most likely point of occurrence for an arc fault. Of course, another distance which could be observed for a less likely occurrence of an arc could be the line to line distance. Before we start our discussion of high voltage physical behavior, we can shed some light at some of the background papers which cover the past decades, provide the foundation to the later works which established the current methodology used by ETAP ArcFault. We always understand that arcs have been studied for many decades for different purposes at different levels. First, we can start by discussing the important work which Warrington, in its famous Warrington formula, which was developed and it stood for many decades, and it provided a fundamental relationship between arc current, resistance, and how they could be used to determine different equipment parameters in equipment design. These equations are still in use and were developed for the use in high voltage circuit breaker applications. Decades later, the works of German researchers such as Turbines and Konglin of the FGH Mannheim laboratories provided the foundation to what we call in ETAP ArcFault Method 1. Method 1 in ArcFault, as you guys will see in future slides through this presentation, is called the Turbines-Konglin arc flush method, and is suited in particular to the IEC standard application. Turbines and Konglin experimented with long single-phase arcs in open air and were able to derive a relationship between the gap, arc current, arc voltage, and resistance. However, the main and most accurate method used by ETAP ArcFault is not based on their work. It is actually based on the utility industry high voltage long arc research performed by the Electrical Power Research Institute, or otherwise known as EPRI. This took place at different labs in Canada and the United States. Their testing which included hundreds of tests, served as the validation to several commercially available software products, including ETAP ArcFault. This method is what is currently called ArcFault Method 2 and serves as the default method for ArcFault simulations in ETAP. So to recap, ETAP ArcFault utilizes different arc current, resistance, and voltage methods to represent the behavior of the electrical arc for different combinations of voltage fault current, gap between conductors, and approach distances. Now, let's focus our attention to the most common and most important type of arc fault model. The line to ground arc fault, as I mentioned previously, was the choice test condition to develop the equations used by ETAP ArcFault method number 2. And it is currently the arc fault or arc flash mode of failure that is required for analysis by Osha and is commonly mentioned in the National Electrical Safety Code standards. What is a high voltage single phase line to ground arc fault in open air? Well, here are a couple of videos which you can watch and are available online for your personal references. You can watch these videos and look over some of the methodology, the actual test procedures and setups, and understand in real time the actual behavior of electrical arcs. After you have the opportunity to watch some of those videos and get some of the physical background of how they behave, you can look at the end results of performing these tests. The end result, of course, of this test is to be able to capture the waveforms of the arc current and arc voltage as they occur throughout the arc duration. Once these waveforms are recorded, mathematical filters and algorithms can be used to understand their physical behavior and to convert their behavior into empirical equations that can be used to represent their relationship over different types of gaps and fault currents. Here we see another measurement, and the reason we have this particular example is because we are now seeing a three-phase open air arc fault. What's important about this is that we can compare this over to the previous example where the behavior of the arc voltage seemed to resemble that of a square wave. Here we can see that whether it be a three-phase open air arc fault or a line to ground arc fault, the arc voltage behavior appears to follow what could be roughly approximated as a square wave. This is of importance in the development of the ArcFault models that are utilized. Here are further examples of research and work where the arc voltage as a function of time, the arc current, duration, and the power recordings can help engineers come up with empirical models which represent the behavior of the arcs. This slide is an example of the post-measurement filtering process that can be used, or was used indeed, by different researchers and organizations to develop the mathematical models that represent the arc faults. Here we can observe the actual measurement, which represents a square wave with the different levels of harmonic content. Once that measurement is sampled and processed to through fast Fourier transfer analysis, we can decompose it and obtain the different harmonic orders. Once we have the harmonic order information, we can develop root mean or RMS equations to represent the arc voltage and current. In this quick video, we will be able to observe the behavior of a long arc in open air. As we can see, as the arc initiates, it stays pretty close to the pilot wire that was used to generate it. And as the arc evolves, it expands, it goes through some elongation effects, and then the hot gases and partially molten materials expand, forming a plasma cloud. This plasma cloud expands and will engulf the electrical personnel, which could be located around the equipment. Let's take a more in-depth analysis of what's just happened in this video of a long arc fault in open air. The parameters which we kind of observe from the video include the distance across the insulator, or what we call the gap length. It is actually not the actual length of the arc, but we can use it as the starting point in the equations to estimate how the arc evolves and elongates throughout the arc duration. The other parameter which is less of importance is the actual voltage, and that actually determines the BIL rating of the equipment and the electrical distance between face to ground and line to line distances. Of course, the voltage will determine these distances, which in turn determine how long this arc will elongate during its duration. As the arc proceeds further in time, it elongates and expands, and it continues doing so as more further cycles of time go forward. And then eventually, as the air around the arc ionizes and starts to convert molecules into ionized particles, we have this plasma cloud that forms around. This plasma cloud and heat that comes from it are of important interest in the heat flux models that are used to represent the behavior. In the case of long arcs, this heat flux model is better approximated by a cylinder shape. As a person or a surface area at a certain unit distance away from the arc fault location will experience different amounts of heat, and the length of the arc will be a very important determining factor into how much energy reaches that surface area. Of course, this is opposite or counterintuitive to the classical models to which people that are in the IEEE 1584 world, where the faults go up to 15 kV and are of gaps in the range of fractions of an inch to 5 or 6 inches. In such short arcs, different models of heat expansion and heat flux could be used, which could be better represented using a spherical approach. Even for similar amounts of fault current and fault durations, a shorter gap length arc will emit less energy towards the unit surface at the same working distance as the previous case on the left hand side. The end result is that the heat flux of longer arcs will be greater than the heat flux of shorter gap length arcs. This chart represents the collection of tests that came about the different research done at different laboratories. They represent how the arc voltage varies as a function of both the gap and the available voltage for current of the circuit. All of these hundreds of tests combined were used to validate the available models for ArcFault simulations. To summarize this arc physical behavior, we can only take some of the key points that we have discussed. To actually learn all the arc physics and the details of the model development will probably take us a few hours. However, we can summarize that high voltage arcs have predictable behavior which can be approximated with mathematical relationships, and we can derive empirical equations from such. High voltage ArcFault waveforms are well behaved and can be used to derive equations which can be either derived from their harmonic spectrum or other techniques. High voltage arcs are also mainly influenced by the short circuit current and the gap between the electrodes. The open circuit voltage or circuit voltage has little effect, may in fact be less than 5% in the overall incident energy in the high voltage systems. The arc voltage changes with short circuit, current, and gap. And this is a very, very important item to remember because the ArcFault models fundamentally allow us to simulate how the arc voltage changes as a function of gap and current for different conditions. The heat flux is of course depending on the gap length as I showed in previous slides. Now let's talk a little bit about the ArcFault model validation. ArcFault was validated, of course, based on the EPRI research work, which in fact was created to validate some of the available mathematical models used by engineers to calculate incident energy in open air line-to-ground conditions. ArcFault was compared to different sources, which included Alan Privet's Duke Heat Flux Calculator, or ArcPro, and other available private calculation methods. We also used the National Electrical Safety Code tables as a reference only, just to see if the ArcFault results were within the range of values provided in that table. Of course, ETAP ArcFault is not a table method or derived approach. It is a full calculator of the arc physical behavior, including the heat flux at a certain distance from the point of the arc fault. We also use IEEE 1584 incident energy results to validate some conditions for open air three-phase fault arcs, and we use countless IEEE research papers and other sources. All combined, ArcFault can be assertively guaranteed to provide reasonable incident energy results as stated in OSHA 1910-69 Appendix E. Some of the examples of the validation against third-party software include comparison against a very common program called ArcPro. Here in this slide, on the left-hand side, we can see ETAP versus ArcPro results, and we can see that there's a very small difference in the results. This chart on the left-hand side shows the heat energy or the heat flux in calories per second per centimeter square. Here's another example, and in this case we're actually using the incident energy for different fault durations. Again, at different working distances, both models provide literally interchangeable results within any kind of conservative safety margin. Further comparisons, like I also mentioned, we use tables 410-2 and 3 of the National Electrical Safety Code C2 2012-2017, in which we approximated the conditions described on the table. In particular, the footnotes where the information about the gaps and the actual working distances that were utilized, and after inserting those parameters into ArcFault, we got various results within the estimated 4 calorie, 8 calorie, and 12 calorie systems. While doing this, we decided to also introduce some of these other third-party softwares in the comparison, and we observed that they're all within a reasonable error boundary as far as the results are concerned. This is of particular interest because we can see that the highest error difference at different conditions was no more than 1 to 1.5 calories. The long bars represent a comparison of the Lee method, which at one point was recommended by IEEE 1584 as an alternative method for performing incident energy calculations in systems above 15 kV. This, of course, is not longer supported, and as far as I believe, is no longer even recommended in the next IEEE 1584 standard. Several comparisons were made, 4 calorie, 8 calorie, 12 calorie systems, and all consistently showing results within a very small margin of difference. So after all this hundreds of comparisons and validation tests against different models, we have arrived at the conclusion that ETAP ArcFault provides incident energy results for open air line to ground conditions within the reasonable margin as specified by different sources and standards. Using some IEEE research and publications, we could also see similar comparisons that researchers in the industry have done, where we compare the Lee method, IEEE 1584, Duke, ETAP method 1, method 2, and we can see, similar to the previous comparisons, ETAP method 1, 2, ArcPro, Duke heat flux calculator are all within the same boundary conditions as far as the differences. Of course, the Lee method being extremely different from all of them. Okay, well, that gave us a summary of the model validations, but now enough talk about the arc physical behavior and the model itself. Let's actually show the program and how it behaves within the ETAP family of ArcFlash products. This particular system in ETAP 18 shows a transmission system delivering power across different utilities, different industrial sites and manufacturing facilities. So let's take a quick look at the overall layout, where we see different industrial plants, different generation facilities, different utility connections scattered throughout the electrical grid. This particular example is good because we have different voltage levels. Let's look at some of the voltage levels available where we can introduce the ArcFault module. We have an open air substation with 132 kV or 132 kilovolt transmission systems feeding the substation. Other portions of the system show 220 kilovolt transmission lines and different locations. Some of these locations are going to be used for the analysis of line to ground arc faults, as we will show in a few minutes. But before I actually get to the demo of the program, let me show you how it is integrated into the ArcFlash products. So once you switch into the ArcFlash calculation, you'll have your choice of methods by simply going into the study case. So for this particular example, we have created study cases related to ArcFault and also for IEEE 1584 or Lee or other available methods. So let's go ahead and inspect an ArcFault created study case. So we can simply click on the suitcase icon, and after we get the study case open, we can focus on the method tab. Here, under the ArcFlash method tab, we can see that there are three options: the NFPA 70E Annex D 2 and 3, which is a very old method, pretty much superseded by IEEE 1584 2002. We have the actual 1584 calculation methodology, which no longer has a year attached to it, since the new ArcFlash method for 1584 will be out hopefully sometime this year. And we have the ArcFault methodology. As you guys can see, by switching between the options, the study case reconfigures itself to the options available for each calculation. Since we're talking about ArcFault, we can observe that now we have the mode of simulation, ArcFault, line to ground, line to line, and three-phase. We also have the selection method, and as I mentioned during the introduction and background on the methodology, we have method 2, which is the EPRI high voltage arc flash work, and once you click on it, you'll be able to see and have direct access to the equations, to the voltage gradient coefficients, thermal flux coefficients, and all the different parameters that are used to get the behavior of the arc. At the same time, since it's fully integrated into ETAP, you'll have the ability to specify how the arc duration, or also commonly known as fault clearing time, is obtained for ArcFault. Just like for 1584, the program automatically determines the protected device operating time. Now, one thing that will become obvious as we see during the simulations is that ArcFault not only responds to phase over current protected devices, but it also responds to any kind of positive, negative, and zero sequence protected devices, which is typically what occurs when you have a line to ground arc fault in a power system. The remaining options for parameters such as automatic gaps, working distance, typical values, incident energy levels for providing a range of the energy at different circuits, they're all available and are part of the ArcFault module. So all the nice tools for automatic data selection, they're all available for the module as well. Okay, let's take a quick look at one more editor before I actually show you how the program works. The ArcFault program relies on a couple of different editors, which we're going to talk about next. In particular, the ArcFault minimum approach distance. This editor, it's a summary of the recommendations in the National Electrical Safety Code related to the minimum approach distances for energized work on line to ground and line to line circuits. What's really important here is to also recognize that these distances vary as a function of the transient over voltage conditions which could occur, and it's very common in distribution and transmission systems. Sources of transient over voltage conditions include lightning, the operation of protected devices as loads are added or released from the electrical grid, and so on, so forth. And once you determine the level of over voltage conditions, which are all included within the program, you can see that these distances vary. So for lower voltage conditions, the distances are smaller or shorter. Therefore, the typical gaps and working distances will be less, and therefore the energy values will be calculated accordingly. All of this comes included with the ArcFault module and is integrated into the ArcFault calculations. Next, what we'll do is we'll actually launch the simulation, and we'll launch it in a couple of different ways. I like to start by faulting a few hundred locations. So by simply selecting a previously created study case where we have several locations through our transmission system, we're going to proceed to do an ArcFault analysis for line to ground conditions throughout this grid. So as soon as we select this, we can proceed to select a particular report and perform a simulation. While this simulation runs and performs these hundreds of analyses, which include the operation of protected devices and different elements throughout your system protection, we can see that the program has now performed all this analysis, and similar to our previous ArcFlash modules, it provides annotations for results right on the one-line diagram that show us the incident energy and the other results such as the clearing time, the ArcFlash boundary, and the working distances. Of course, this 48.4 inch is calculated based on the typical gaps and application voltage for this particular line, based on the National Electrical Safety Code recommendations and equations. Okay. As we can see now, of course, we've faulted hundreds of locations, and of course, I know we will expect to have a powerful filtering analysis tool just like we have for ArcFlash using IEEE 1584. So if we proceed to open the ArcFlash analyzer, we'll be able to see that all the tools available for ArcFlash using 1584 are also available for the ArcFault module. We see all the different voltage values. We can see the incident energy values filtered and sorted throughout the system. We can choose to focus and filter onto higher energy areas or trouble areas for different conditions, and all the familiar filters and analysis tools that are provided by ETAP in the ArcFault Result Analyzer. Labels and reports, which of course are less common for the high voltage ArcFault world, are also available but are expected to have less use because it's not really common to provide labels for open air transmission systems. Now let's proceed to show a simulation of the operation of protected devices. Let's zoom out into a particular portion of our system where we have a couple of transmission lines, 220 kV lines, and we're going to switch our study case to perform a single arc fault on either one of these two parallel 220 kV lines by simply clicking on the fault insertion for three-phase line to ground, line to line, or three-phase arc faults. We can click on it and drop the fault on any location we want. In this case, I'm going to be faulting it on bus 63, which is a location along this 220 kV transmission line. As we can see, the operation of the two protected devices at the substations on either end of the transmission line, and after both devices operate, we have the de-energization of the arc fault. We can reduce the speed of the flashing down to 0 so that we can focus now on the results of the simulation. What I would like you to pay attention to is the displayed currents and results on the one-line diagram. We are currently displaying the sequence current values, which represent positive, negative, and zero sequence currents which would flow in that transmission line system in the event of a line to ground arc fault, including the effect of the arc resistance and arc voltage. We could easily switch to the phase values. Now we have phase A, B, and C fault currents. Or we can switch to the zero sequence currents only to determine what part of our circuit has grounded elements and which one doesn't. All combined, this positive, negative, and zero sequence currents can be used to determine the operation of both phase and ground protected devices. As we can see from our ArcFault viewer, a fault at this location has caused the operation of two types of protected devices. On one end, at one of the substations, circuit breaker 101 was stripped by relay 4 using the ground over current 1 instantaneous function. On the other end substation, with circuit breaker 880, the fault was cleared by the operation of relay 2 using a phase over current type 51 protection. And the end result is that the ArcFault was de-energized. In this case, 2 sources were energized in the fault. After both sources are de-energized, the fault is clear. Now, there is a tremendous value to being able to analyze the results from the point of view of the operation, because obviously transmission and distribution systems may involve some complex operations for their protected devices. So this gives you an idea of how ArcFault simulates different kinds of faults. In future examples throughout this webinar, I'll give you some cases that involve other types of arc faults, such as line-to-line and line-to-line-to-line, or three-phase arc faults. To summarize what we have just learned during the actual simulations of ArcFault in ETAP, we can take a look at some of these slides. As I mentioned during the simulations portion of this webinar, ETAP has several ease of use features integrated within the tool. The auto gap for line to ground arc faults is based on the National Electrical Safety Code C2 2012 and 2017 editions, and it provides a set of typical values where the user can select values for the gap based on the tables provided or based on equations. As we can see in this slide, the program allows you to either use a set of predetermined values up to 46 kV, where you can define the individual gaps to be used, or typical gaps, or you can let the program use equations provided in this standard to determine the typical gap for a line to ground arc fault. At the same time, you may also choose to do a less likely but still possible line-to-line simulation, and therefore you may need typical line-to-line gaps. So just like I mentioned before for line-to-ground, the program provides typical values for line-to-line situations. Another very important data entry factor is the working distance. ArcFault provides an automatic working distance selection tool, again based on an ESC C2, and based on the voltage levels, the program can then use the minimum approach distance face to ground with or without tools as provided in the NESC C2 tables to determine a typical working distance for line to ground condition. Now, whether the task is going to involve tools or not, the program will give you either set of working distances, which can be used directly for the calculations. Of course, you also have the ability to directly enter a user-defined working distance for the simulation. Just like for line to ground, you have typical line-to-line working distances. Let me also add to this slide, and as we will see in the next few minutes, that there may be other typical gaps and working distances for conditions such as three-phase enclosed equipment. Of course, those gaps are outside what has been published in standards like IEEE 1584, So as part of the development of ArcFault, ETAP also provides a set of typical values for gaps and working distances for such equipment to allow us to calculate the incident energy in renewable energy system collector systems, as we previously mentioned. While I was showing you the typical approach distance editor within ETAP, I also mentioned the capability to account for the transient overvoltage condition. So based on the requirements of Osha 1910 Appendix B, there may be different approach distance requirements based on the transient overvoltage conditions. ETAP has different sets of transient overvoltage values integrated, which can be used for the selection of this working distance. Of course, when I show you the editor, I mentioned that there may be different conditions where the transient overvoltage values would change depending on the electromagnetic transient response of the voltage in the transmission system. Once the appropriate transient overvoltage value has been selected, you can use this to derive the working distances to be used in the ArcFault simulations. Next, we can actually discuss a little bit of how ArcFault can also be used to perform arc flash analysis for renewable energy collector systems, in particular three-phase enclosed equipment. As we can see in this slide, we have an example of a very common renewable energy collector system where we have each individual turbine of different sizes, for example 1 to 2 megawatt wind turbine units scattered throughout the wind farm at different locations. Each of these wind turbines will have a step-up transformer, which will then send power through the collector system out towards a AC open-air substation before the point of interconnection for the transfer of power to the utility or grid. What's important to note here is that typically these transformers are placed at different locations, the most common of which happens to be open-air enclosed configurations placed on pad mount areas or pad mounts. For such, this equipment placed in open air still presents an arc fault situation where you have typically three phases incoming in the collector system, and where you also have exposure to the low voltage side, operating typically between 600 to 900 volts AC. Of course, for the low voltage part of the system, we have classically used the IEEE 1584 model. That model has been used by the industry successfully for the arc flash calculations in this area for many decades. The problem is that models were not really available for longer gap arc flash events in the medium voltage collector side of the circuit. For these bigger boxes and longer gap conditions, the models of IEEE 1584 and also the Lee method, which is used by some engineers to perform analysis, may end up producing overly conservative results for the incident energy calculation. Because of this, enclosures around wind turbines of different sizes, we have developed a model that can extend the IEEE 1584-2002 equations into this domain. We have also added capability for the ArcFault module to handle this type of equipment. As we can see in this slide, the first choice that you'll get when you obtain the ArcFault module is to use an extension of the IEEE 1584-2002 with, of course, variations on the gaps and also the enclosure sizes. This is important because at these voltage levels, the gap between conductors will be longer. As we can see in this table, we see that we have a pretty continuous increase in the amount of energy produced for similar fault current values. For an available short circuit current of 20,000 amps and an arc duration of 200 milliseconds, we get consistently a current close to the available short circuit current, so very little decay or reduction in the current because of the arc resistance. However, what we can observe is an increase in the energy produced by the arc with longer gaps. This is the main principle that gives us confidence that the IEEE 1584 method can be extended to give enclosed results at this voltage range. Here are some of the IEEE references and papers that were used for the application of both ArcFault enclosed simulations and the extension of the IEEE 1584-2002 model for this equipment. ArcFault was extended using the principles explained by Wilkins in his reflectivity coefficient analysis, where he basically describes the reflected heat energy from a three-phase ArcFault inside of an enclosure related to the dimensions of the enclosure itself. Based on the opening area and the distance and positioning of the electrodes within that box, Wilkins was able to provide some reflectivity coefficients that allow us to determine the energy reflected towards a surface positioned in front of the opening of the enclosure. Using these principles of thermal heat reflection and using different papers and test results available throughout the industry, the ArcFault enclosed three-phase faults were configured to reflect potential variations in the energy for some special conditions. So what you will expect to see when you use the ArcFault enclosed simulations is a more conservative set of results to account for some statistical events where the incident energy could be higher than what is predicted by the IEEE 1584-2002 model when applied to this particular equipment range. This particular chart shows different test samples, which are variations of box size, gaps, fault current level, etc. And for these variations in these parameters, we can see the correlations of the energy values for the different methods that we have available in ETAP. Next, we can actually see some ArcFault simulations in these renewable energy collector systems so that we can understand how to configure the different options within ArcFault to give us some incident energy estimation for these kinds of systems. In this particular system, we see an example of a wind farm with a set of wind turbines and a collector system interconnected to a power grid. For the purpose of this discussion, we really don't have time to go over all the details of how ETAP models the wind turbines of different technologies. However, I can quickly mention that in ETAP 18, we have added a large number of capabilities related to renewable energy systems. Examples of such capabilities include the short circuit model for different types of wind turbines, which have voltage and current regulators. So full inverter or full converter wind turbines have a new short circuit model page where you can model the behavior of the fault current. Also, we have added a frequency write-through or reactive power control set of parameters on the element itself. However, for the purpose of ArcFlash, the most important feature is the automatic trip time and shutoff of the wind turbine, which is a time-based protective functionality that will automatically trip the wind turbine from the system if the fault persists for a predetermined amount of time. With all these features, we can perform some simulations in our wind turbine system. We'll focus in an area where we have the step-up transformer. And with this step-up transformer, which I'm highlighting currently, we'll have both a primary side and a secondary side at the low voltage of the wind turbine. Of course, as I mentioned during the previous slides, we're focusing on the 34.5 kV collector system. So first, what we'll do is we'll perform an arc flash using the theoretically derived Lee method to observe what's the energy that we get for a fault at that location. So we'll proceed to place a fault insertion and place a fault on that location. And we'll, of course, get a warning that indicates that the theoretically derived Lee method is being used for this location, and that it is recommended to look for alternatives like ArcFault to determine the results as such. We'll select our library and proceed to obtain the results. As we can see, as far as the short circuit current, the response is fairly accurate because, as we know, the full current in the Lee used by the Lee method is pretty much the same as the available short circuit current. So we don't expect too much of a response difference time. However, the main difference comes in the incident energy, where we will be able to see that the value is significantly higher than what we'll get with the next simulation modes. In this case, we observed 37.6 calories at a working distance of 36 inches, which is typical for this kind of equipment. So if we now switch over to the other option, which is the extend the IEEE 1584, as I mentioned during my previous slides, we can configure ETAP through the options preferences, and we can select the option called extend IEEE 1584 for equipment up to 36 kV. Once we enable this option by setting it to its true value, we can proceed to repeat the same simulation, and now we can observe the results. At this case, we see a significant decrease in the energy to a more realistic number, 3.32 calories at 36 inch for a 133 millisecond exposure time. Last, we can observe how the ArcFault method will behave under a similar condition. If we select ArcFault, three-phase fault, and our default method, method 2, and also make sure that this location has been configured as a enclosed equipment with width, height, and depth, and reflectivity coefficients which match the characteristics of the equipment that we're modeling, we can proceed to perform the simulation using the ArcFault module. And as we can see, in this case, we have a slightly more conservative result of 7.8 calories per centimeter square at 36 inch. This gives you an idea of how you have now a set of options to model incident energy results for this kind of equipment. Next, I would like to show you a different tool which can be used to analyze these ArcFault conditions for this equipment. If you click on the calculator symbol within the ETAP toolbar, we can get our new and enhanced power and arc flash calculator. And these tabs, including AC and DC, will be the topic of future webinars. Of course, the one that we like to focus for this part of this webinar presentation is the ArcFault tab, where we have added different options and methodology to visualize the ArcFault results. This calculator will be available in ETAP 18.1, in the very next version of ETAP due in a few months or a few weeks. With this tool, which will be available with the purchase of the ArcFault module, you can do a lot of things, including visualize the effect of the working distance automatically. And as you can see, as we vary the working distance between the point of the fault and the location of the electrical worker, we observe different energy values. We can see that as you approach the arc fault, we see higher energy values represented with different colors. Of course, this tool will have the ability to automatically tell you the results. As soon as we vary the current, we can see how parameters like the arc fault, current, voltage, resistance, the voltage gradient, and the arc power vary as a function of the current. So as we can observe, like I mentioned during the background of the methodology, the current seems to have a dominant effect on all of the arc power behavior and arc energy values. Similarly, the gap has another dominant effect, like I mentioned before. I also mentioned that the nominal voltage will have little effect, and as you can see, other than the actual equipment that you're modeling when you're placing arc faults, there is really not too much effect on the energy and arc current values that are determined by the program as I travel through different voltage values. Of course, in the previous discussion using ETAP, we were going over the effect of enclosures versus open air and three-phase faults inside of boxes in renewable energy systems. If we switch our equipment type to a switchgear, now we have, similarly to what I showed in the actual ETAP simulator, we can observe the equipment sample image change to the enclosed configuration. We see the energy value, and we can see the reflectivity factor, which is the ratio of the open air incident energy versus the energy in the presence of a box. This calculator also gives you the ability to visualize the results as a function of a contour plot. So if we switch back to the open air condition and we click on the contour plot, the program is going to generate a set of curves which represent the heat flux pattern as a function of distance, where the warmer areas represent the areas where the energy transitions from a heat flux of approximately 25 to 40 calories per centimeter square towards 8 and less than 8, and transitions towards around 1.2 or less. This could be useful to visualize the heat flux in different areas around the element. At the same time, we can see the heat flux versus distance plots. We can see the incident energy as a function of working distance, or we can see the incident energy as a function of time. When we click on the time slider, we can see, of course, that as we let that arc fault persist in the system, we're accumulating far more energy. Another important feature of this calculator is that it's packed with typical data values for the working distance, for the gaps, for equipment types, and so on. And it also allows us to visualize the relationship between the shock approach boundaries, the minimum approach boundaries, and the actual arc flash boundaries. As we can see, when we click on the typical value, we see the curves in green and blue color change as we change different voltage values. As we can see now, the minimum approach distances have increased because of the higher voltage levels. This tool also includes a very nice feature which allows the ArcFault tool to be interconnected with external databases. The batch process tab of this calculator will allow the interface to a database where the user could specify the fault current, the clearing time, the gaps, different arc flash boundary distances, different working distance requirements, and so on, and all the different parameters that define the value. Let me give you an example of how this works. First, we can select the import database. An example of that is provided with the tool. We can import the data, and once we've imported it, we can actually visualize the data to observe what it contains. We can see that the data includes the location, the bolted fault current, the type of fault, whether it's line to ground, line to line, or three-phase fault, the nominal voltage of the system, the gap, 3 different working distances, because the working distance is a highly variable factor in open air transmission systems, an expected fault clearing time, 3 different arc flash boundaries where you can get the distance at which the energy would be at 1.2 calories, 4 calories, 8 calories, and so on. If the equipment happens to be enclosed or open air, you can identify and provide the dimensions of the equipment, along with correction factors which can be used to apply the ArcFault model to 3-phase faults. Now that we've inspected this input data, we can quickly see that it contains somewhere in the ballpark of 3,000 or more records, which we're going to analyze using the batch process tool. Next, we can simply select the location where we want to export the results. We can inspect the file and observe that it's an empty data file. And now we can proceed to calculate. Right now, the ArcFlash calculator is going through 3,000 iterative solutions. Each iterative solution takes approximately 1,000 sub-iterations, which are performed very fast to determine the actual arc current, resistance, voltage, and all the physical characteristics of the arc, as we discussed at the beginning of the presentation. I click on the OK, and now we can quickly view the results. As we can see, the output of this batch calculator provides different columns that show us the headers and the results. So for example, we can observe what are the energy values. We have the flux, the energy, the arc energy, the instant energy at the first working distance that the user specifies, second, third, and so on and so forth. We also see the voltage gradient, any statistical adjustment factors, any reflectivity ratios, and so on and so forth. Plus, the batch calculator will also give you a list of all the potential warnings or conditions of special interest. So in case there are errors in the data or input parameters, errors such as the current being outside the limits of the model, or the voltage being below the voltage limits of the model, or the gap being outside the range, and so on and so forth, the program will give you a list of all the problem conditions so that you can go back and make the corrections on the data entry. All in all, this calculator can interface with third-party software where the currents and clearing times could also be obtained, and the ETAP ArcFault tool could be used to obtain the results very quickly and efficiently. So to recap and to summarize the presentation, the ArcFault module contains both a network simulator, as I showed earlier, and also a powerful calculator which allows the user to visualize the results and perform quick what-if simulations. The ArcFault module also provides the arc current, arc voltage, arc resistance, voltage gradients, arc power, energy flux, energy power, and any kind of statistical adjustments as recommended by the models which it applies, so that users can perform mainly line to ground arc faults in open air overhead distribution systems. With this, I think I've taken enough of your time, and I would like to thank you for attending today's webinar. We'll be around for a few minutes where we can answer questions about anything of your concerns, questions, any comments, and of course all the references and methodology information is provided in the documentation that is provided with the purchase of the ArcFault module. It's been a pleasure to give you this webinar today, and I hope that you can join us for our next webinar, which is going to be related to the new IEEE 1584, hopefully 2018 model. Thank you very much.